afternoon. No ladies, so only the gentlemen. I guess it's quite obvious here who am I. I cannot be Mathias Silmbroth. I'm Sheikh Enamul. Before I get to the topic, I will give you a short background story. So like everybody else, we are also doing research on additive manufacturing. And we have one research group which is continuously growing. They're solely devoted to wire arc-based additive manufacturing. They are focusing on many different issues in this manufacturing process, but someone last year, one of their industry partners, proposed, hey, why don't we try the crashworthiness application, how they work out. So they said, okay, let's do it. So we manufactured a couple of crash boxes, some generic crash box, did some crash tests. And also, they wanted someone to simulate the crash test. And here I come to the scenario. I'm a simulation engineer, and I belong to the numerical simulation team. So I did the simulations. And in order to do the crash simulation, I need a material card. So in this context, we need actually a plasticity model and a ductile fracture model. So in the next couple of slides, I will briefly show you how I calibrated. So it's not really a fundamental research, it's pretty much standard engineering practice, but from the material point of view, probably it's a little bit new. So I will not read the content. The generic crash box that I mentioned, you can see from the very left side. This is how it looks like after manufacturing. Then we cut at the top and the bottom. And we had three variations. The first one was not milled or not machined, which is our most preferable variation because we do not want to spend time and money for doing the machining and so on. But we also wanted to try out the other two variations. So in one case, we milled the outer surface to make the thickness a bit more consistent. And in the third variation, we milled both surface, outer and inner as well. As a result, in the third case, we have a constant thickness, and there is no wettiness on the surface. We did the crash test. You can see the crashed profiles, at least one of each variations, and the force displacement curve. So the result is not really what we wanted to have, because in a metallic material, when we have axial crash and we want the structure to absorb energy, we want nice plastic folding. So each, like a sine wave, each folding represents one wave, but here we didn't have that. So that means we need to work more on the alloy point of view at least. But what we also have seen that the one which was not milled was not really consistent, so the test data is not really repeatable. The other two was quite consistent. So for the sake of simplicity, or as a first attempt, I moved on with the third variation, the both side milled. Right. Here you can see the experimental characterization. So on the very top left corner, it's a standard uniaxial tensile test specimen. Everybody knows this specimen. And from here we get the hardening curve, the Langford parameter. And what we have noticed is there is a mild anisotropy in the yielding behavior. So the Langford parameter, at least in one direction, was around 1.1. The other two directions we don't know because the specimens were small and we couldn't measure the Langford parameter for such a small specimen. For the hardening, we have seen in all three directions the stress strain behavior were similar. So fairly, I think it's safe to assume it's isotropic hardening, but don't confuse it with the isotropic kinematic hardening. This is not what I meant. Here, isotropic hardening means the hardening behavior is independent of the direction. But what we have noticed, which is a little bit scary, is the scattered fracture and also a little bit anisotropic fracture. So that's not really a good thing from a numerical characterization point of view. Additionally, I have 4 more test specimens you can see here from left to the right, it covers a stress state of, let's say, starting from shear up to equibiaxial stress state. It's a standard testing program. What we have noticed here is, first of all, the material is quite homogeneous, so all the specimen tests gave us more or less similar force level, but we have seen some scatter in the failure again. That's also not really desirable for a numerical simulation point of view. But so now what we have, mild anisotropic yielding, indication of scattered fracture, and an indication of anisotropic fracture. However, instead of addressing all the difficulties at once, we decided to go on. There is a saying that make your simulation model as simple as possible and as complicated as necessary. So I wanted to calibrate a von Mises plasticity model without considering this mild anisotropy yielding, and also for the failure, a isotropic damage and failure model. So here you can see the hardening behavior. I fitted and extrapolated with the Hoque Sherby. I made two failure models. One is for shell and one is for solid. So when we simulate with shell elements, the failure strain is a function of stress triaxiality, so that's a curve. And when we simulate with solid elements, then the failure strain is a function of triaxiality and the loaded parameter, so it's a surface. The damage model is the standard damage model implemented in a commercial code, LS Dyna. Maybe you have heard of Gizmo. And for the fracture curve or fracture surface, I used the Hosford-Coulomb failure criteria, which was proposed by Professor Philippe Moore from Zurich. What else to mention? Well, for the shell elements, I had to do some regularization. It's a simplified trick to get rid of the mesh sensitivity. Sometimes works, sometimes doesn't really work very well. For solid, I didn't have this issue because I had always this 0.5 millimeter mesh, so the coupon and the structure as well. Let's have a look when we simulated using these material curves, how they behaved. So in the middle you can see the crash profile, at least one of them after crashing. And at the top, so on the very left, it's the shell model without any failure model inside. That's why we don't see any fracture. And the right-hand side, the gizmo was inside in the material card. That's why we see fracture. In fact, we see catastrophic fracture. At the bottom, we have the solid mesh, one without any damage model or fracture model in the material card, and the next one including the damage model. And we can see some fracture as well. If you compare the force displacement curve with the experiment, you can see for both cases, for shell and solid, the simulation without any failure model inside over-predicts the force level, which is quite obvious. But the one with the failure model inside, for shell didn't really work out. It's a bit unstable. But with the solid, we were fairly in a good agreement, considering all the simplifications that we ignored the anisotropic yielding. We did not use the DIC measurement to calibrate the hardening curve, or we even ignored the anisotropic fracture behavior. So it is a question, actually, it's a matter of engineering judgment, how much effort we want to put to make a whole experimental characterization and then calibrate the sophisticated damage model to simulate a crash worthiness behavior. Anyway, that's actually in short. I will summarize. So what we have seen is isotropic hardening, so in the isotropic stress strain behavior, direction independent. Nearly isotropic yielding, or mild anisotropy in the yielding behavior. We have seen scattered fracture, so we need further experimental, so more coupon tests to really have an idea or an impression about how much scatter we have in the fracture. we have an indication of anisotropic fracture, but only under uniaxial tension load. If we want to make a whole experimental characterization, then we have to repeat all those shear notched biaxial tests in all three directions and see how it behaves. And in case if it really shows an isotropic fracture, then we cannot use this isotropic damage model gizmo. There is a model which is implemented already in LS-DYNA called eGizmo, which considers the directions, so that could be a possible solution. And then I think it's a typical solid versus shell scenario that, of course, shell elements for thin-walled structures gives us very fast solution and also fairly accurate. But once in a while we do see with the shell elements we cannot capture the reality. And yeah, if we go for solids, then we get a better, or we can mimic the reality better. The question is how much computational effort. So I didn't write it here, but with the shell model, the simulation took roughly 15 minutes using 64 CPUs in our cluster, and with the solid it took roughly 12 hours. So you can imagine the difference in computational effort.
1 minute.
Okay.
You are in time.
I have to thank the funding agency, but I think nobody from the funding agency is here, so I can skip the slide. And thank you very much. If you have any questions.
Are there questions?
Yeah, interesting presentation. I have a question about the applications.
Yeah.
You mentioned, or maybe I did not get, what's the application for this kind of thin wall WAM part?
It was a little bit optimistic, so they thought about crash structure in a car. Maybe a crash box.
And what's the material?
The material, it's commercially available alloy, aluminum 5183.
Okay.
So you can buy them in wire form, and then we just manufacture with a wire architecture manufacturing process.
Okay. So that's the potential application, or you got a question from industry, or it's a kind of assumption that you considered in the beginning?
It's a very, it was a request from the industry partner. It was not really a standalone project. In a project, we had some money and time left, and they said, okay, let's try it out, how it works. Because for crash application, usually we use extruded aluminum profiles,
yeah.
Right?
Yes.
And the manufacturing process, the wire arc is very slow and time consuming, right? But for certain cases, if I remember correctly, for trains or S-Bahn, U-Bahn in Germany, for example, if they have to replace some existing structure, they don't want series production. So for those special cases, maybe they could go for some additive manufactured part. But this is not really, or this is not going to be let's see, what to say. This is not going to replace the extrusion. There is no way to replace the extrusion process. Yeah.
Okay. And if I may, I have another question.
I think that there was another question from behind.
I'll pass.
If we have, take your.
I have one question as well. Thank you for your presentation. The parameters for your damage model were determined from experimental characterization.
I'm sorry, I didn't.
The parameters for your damage model
Mm-hmm.
were determined from experimental. Were determined experimentally. You done experiments.
Mm-hmm. Yeah, exactly. Because this is what I have shown here. So these are the specimen tests to calibrate the damage model. You do not get the parameters directly from the experiments because it's a shear test, but the strain, it's not really failure strain under shear. The strain path is not straight, linear, yeah, it deviates. So what we have to do is we have to simulate each and every specimen and calibrate either this curve or this surface, depending on are you simulating shell or solid, until you see the, okay, it's not very clearly noticeable, but until the force displacement curves fit each other, and the failure in the simulation occurs at the same time when the failure happened in the experiment.
And you transfer these model parameters to the model of the part of
Yeah.
the component.
Exactly.
Okay, we have no room for other questions. I'm sorry, but you can use the coffee break time or other time during the conference.
Okay.
So, thank you very much, and we can.